Hi everyone. So recently, for work-related reasons, I had to film a series of videos covering basic operation of our Helios Nanolab 600 dual beam scanning electron focused ion beam microscope, and I thought it would be a good idea to compile all those videos into one longer video that covers all the elements of basic operation of this instrument. I know there have been quite a few requests for a tutorial on using fib for lamella preparation for TEM, and unfortunately this video isn't going to cover that, but it is going to provide the basic framework for using this instrument, which will be sort of a prequel to what you would need to know before you're going to use it to make lamellas for TEM analysis. I do want to, of course, let you know that I do intend on preparing that tutorial video covering lamella preparation, because I know that's probably what's been most requested to this point. So I hope you enjoy the video, and as always, please feel free to share this with anybody whom you feel it will be useful. Please like and subscribe, and if you have any questions or comments, please let me know. Thank you. When starting your fib session, enter the beam control module and select wake up to turn on the ion source. Then select vent to start venting the chamber. Remove the stub holder module from its case. Stubs may be loaded into one of the three triangular positions in the stub holder module. Also note that each position has its own set screw. Remove the stub from its box and place it into the stub holder module in the desired position. Then secure the stub in the module by tightening down the set screw. To load a grid, uncover the grid loader and then remove the grid holder from its case. Note that the grid holder can accept up to 6 grids. Identify the side of the grid holder with the holes, as this will need to be placed face down into the grid loader. Place the grid holder onto the loader, lining up the pin on the loader with one of the holes on the back of the grid holder. Then tighten down the loader to push up the clip and open up the grid holder to accept a grid. Use a sharp pair of tweezers or a set of vacuum tweezers to pick up an omni probe grid for loading into the holder. Note which side of the grid is rounded, as that is the side that should be entered into the holder. Place the grid just in front of the clip. Then tilt up the base on the loader and gently tap on the edge, and the grid should slide under the clip. Then tilt the base of the holder back down and check to see if the grid is sitting level inside of the holder. If not, use a sharp pair of tweezers to carefully reorient it so it is level. Then remove the grid holder from the loader. Use an optical microscope to verify that the grid is not bent. Place the grid holder onto the stage of the microscope. Orient the grid holder such that you are facing the grid edge on. Then focus on the edge of the grid to verify that it is straight. If the grid appears bent, it should be discarded, a new grid loaded, and then again verified that it is straight before proceeding. The hinge on the Omni probe will be fully open when the chamber is vented, or close to being fully vented. Gently open the chamber door. To load a module onto the universal mounting base, note that each module has a set of pins. Line up this set of pins with the indicated set of slots on the universal mounting base. Then load a clamping bar onto the universal mounting base on the other side of the module, making sure that it is properly oriented with the correct side up. Then gently hold it down and then tighten down the screw on the clamping bar. The grid holder module can be loaded similarly into the universal mounting base. However, the grid holder needs to be placed into the module first before tightening down the clamping bar. When you load the grid holder into the module, make sure that it is level. Then place the remaining clamping bar and tighten it down. Gently close the chamber door, making sure it is completely flush with the edge of the chamber. While maintaining pressure, once the hinge is fully closed, pressure on the chamber door does not need to be applied anymore. While the chamber is pumping down, activate the electron beam quad and then select the stage pull-down menu. Then select 0 beam shift. Repeat this for the ion beam quad by activating it, going to the stage pull-down menu, and selecting 0 beam shift. With the ion beam quad still activated, remain in the beam control module and verify that the scan rotation is set to 180. Then enter the navigation module. Under the list of stored stage positions, select Home to drive the stage to the home position such that the modules are directly under the electron beam column. In the beam control module, beams on will be selectable once sufficient chamber vacuum has been achieved. With the E-beam quad activated, select beam on to turn on the beam. Activate the I-beam quad and do the same. Then enter the patterning module. Navigate down to gas injection and next to PT depth, double-click cold to start heating the PT GIS. The progress bar will read warm once complete. Click on the E-beam quad and then select the pause button from the main toolbar to start acquiring a live image. Beam voltage and beam current settings can also be selected from the main toolbar. Use the magnification knob on the manual user interface to adjust the field of view as needed. Use the joystick to move the sample in the X and Y directions. Alternatively, double left-clicking on a position in the image will move the stage to recenter that position in the image. Identify a feature on the surface of the specimen and mag in on it. Then use the focus knobs on the manual user interface to focus the feature as best as possible. Once finished focusing, select the Link Z to Working Distance button from the main toolbar to couple the working distance with the Z coordinate of the stage. Depending on the type of specimen you are using, it may be necessary to align certain features within the electron beam image prior to starting to make your lamella. In this case, we have a single crystal wafer and want to align a cleave edge so it is vertical in the image. Navigate to the feature of interest, then select the stage pull-down menu and then XT Align feature. Then follow the instructions in the dialog box to align the feature of interest. Verify that the electron beam is focused with Z linked to the working distance. Enter the navigation module and enter 4 in for Z to move the stage so the working distance is approximately 4 millimeters. Find a recognizable feature on the surface of the specimen and move it to the center of the image. Then tilt the stage to 26 degrees and note which way the feature moves away from the center of the image as the stage is tilted. In this case, the feature is moving up, which means that the stage needs to be brought down to bring the feature back to the middle of the image. Do this by adjusting the stage Z control, in this case to the left, to move the stage down and bring the feature back to the middle. Then increase the stage tilt to 52 degrees, again noting if any movement of the feature from the center of the image occurs. Should there be any when the tilt is completed, once again use the stage Z control to return the feature to the center of the image. Then return the stage tilt back to 0 degrees. Recenter the feature in the image and then change the stage tilt to 52 degrees. Note any movement of the feature from the center of the image once tilting is done, and if any occurs, use the stage Z control to adjust the stage position accordingly so the feature goes back to the center of the image. Then return the stage tilt back to 0 degrees. With the sample at eccentric height and the stage tilt at 0, the electron beam can now be aligned. Select Direct Alignments from the toolbar. In the Direct Alignments dialog box, select Crossover to enter crossover mode. Then use the crosshairs under Source Tilt to align the spot so it is centered in the image. Then select Crossover to return to image mode when complete. Select Lens Modulator to modulate the strength of the final lens. Then use the crosshairs under Lens Alignment to minimize shifting of the image as the image goes in and out of focus. Once shifting of the image has been minimized, select Lens Modulator to turn off the modulation. Then focus the image and then use the stigmator knobs on the knob set to obtain the sharpest image possible. Note that this is an iterative process and you may need to refocus and restigmate several times to achieve the best possible result. Also keep in mind that alignment of the electron beam is sensitive to the voltage and the beam current selected. If either of these parameters are changed, then the alignment must be repeated to ensure the best image is obtained. Platinum deposition using the electron beam is most effectively accomplished using a low beam voltage and a high beam current. With the stage set at eccentric height with a tilt set to 0, navigate to an area on the specimen that is free of debris. Set the magnification as needed, then navigate to the patterning module, then to gas injection, and then check the green box next to PT dep. The PT GIS will then insert, which will be accompanied by a change in contrast of the image, which can be corrected by using auto contrast and brightness. Then acquire a snapshot of the electron beam image. In the patterning module, select the rectangle pattern and then click and drag on the electron beam image. In the Basic tab, change the application to PT Dep E-beam, and then you can also adjust the X, Y, and Z dimensions of the pattern as desired. Once the pattern parameters have been set, acquire another snapshot. Then click and drag on the pattern to position as necessary, and then select the play button to start the deposition. When E-beam platinum deposition is done, it is standard practice to deposit a thicker strap using the ion beam. Unpause the electron beam image and then select and delete the rectangle pattern. Then retract the PT-GIS by unchecking the green box next to PT Dep. Feel free to adjust the contrast and brightness of the image as needed by using auto contrast and brightness. Return to the patterning module and then set the stage tilt to 52 degrees. If the strip deviates from the center of the image, adjust accordingly using the stage Z control. Then refocus the electron beam image. Activate the ion beam quad and then select appropriate beam conditions for PT deposition. Then unpause the ion beam image and perform auto contrast and brightness as needed. Then use the shift knobs on the manual user interface to shift the ion beam image so the strap is centered in the image and the I-beam is then coincident with the electron beam image. Return to the patterning module and insert the PT-GIS. Then take a snapshot of the ion beam image. Select the rectangle pattern and then click and drag on the image to draw a rectangle. Enter the Basic tab and change the application to PT Dep I-beam. You can then adjust the X, Y, and Z dimensions of the pattern as needed. Keep in mind that for PT deposition to be effective with the ion beam, the current density should not exceed a few tens of picometers per micron squared. Take one final I-beam snapshot and then position the pattern as needed. Then select the play button to start deposition. The progress of the ion beam platinum deposition can be viewed in real time using the electron beam. Activate the electron beam quad and then unpause it. Turning on averaging from the main toolbar will also make the electron beam image clearer. Also keep in mind that live electron beam imaging while platinum deposition or milling is occurring is more effective the higher the ratio of the electron beam current to ion beam current. Select and delete any patterns that may be present in the ion beam quad. Then select an ion beam current to be used for cross-sectioning, which is typically in the nanoamp to tens of nanoamp range. Unpause the ion beam image, perform auto contrast and brightness, and use the focus knob on the manual user interface to focus. Do this as quickly as possible so to minimize the time spent live ion beam imaging. In the patterning module, select the regular cross-section pattern and click and drag to draw on the ion beam quad. In the Basic tab, change the application to silicon. Then go to the Advanced tab and set the rotation as needed such that the thick line of the pattern is closest to the platinum strip. Return to the Basic tab and adjust the X, Y, and Z parameters as needed. Then take an additional ion beam snapshot and then click and drag on the pattern to position as needed. adjust the magnification as needed, and again acquire another snapshot. Then select play to start the pattern. To view a live ion beam signal from the area that is being milled, activate the ion beam quad and then unpause. Then use the contrast and brightness knobs on the manual user interface to adjust so the signal is more visible. Alternatively, you can activate the E-beam quad and unpause to view the milling in real time using the electron beam. Again, keep in mind that this will be most effective the higher the ratio of electron beam current to ion beam current, and also keep in mind that it may be necessary to turn on averaging to make the image easier to see. To perform a cleaning cross-section, activate the ion beam quad and change the current as needed. Then delete any patterns present in the ion beam quad. Unpause the ion beam image to go live, perform auto contrast and brightness, and focus the image as needed. When finished, acquire a snapshot. In the patterning module, select the cleaning cross-section and then click and drag on the image. In the Advanced tab, adjust the rotation so the thick line of the pattern is closest to the platinum strip. Then return to the Basic tab, make sure that silicon is selected under Application, and adjust the X, Y, and Z parameters as needed. Acquire one more snapshot, and then click and drag and position the pattern as needed. Then select play to start the pattern. Once again, you can view the progress of the milling in real time by activating the E-beam quad and unpausing, again using averaging as needed to make the image clearer. To execute a rectangular mill, activate the ion beam quad and adjust the current as needed. Then unpause the image, delete any patterns that may be present, perform auto contrast and brightness, and focus as needed. Acquire a snapshot of the ion beam image. Then enter the patterning module and select the rectangle pattern. Then click and drag to draw a pattern on the ion beam quad. Adjust the parameters as needed, take an additional snapshot, and reposition the pattern as needed. Then select play to start the pattern. A live ion beam signal can be acquired from the area that is being milled, but it may be difficult to see depending on the size of the pattern on the image. Alternatively, you can activate the E-beam quad and image using methods previously described for the platinum deposition, regular cross-section, and cleaning cross-section. When using the omni probe, it is important to keep in mind that it should only ever be inserted and manipulated with the sample at eccentric height and the stage tilt at or very close to 0 degrees. Activate the electron beam quad and unpause to acquire a live image. If the stage is not at 0 degrees, enter the navigation module and tilt back to 0 degrees. When the stage tilt has returned to 0, activate the ion beam quad and reduce the current to something in the tens of picoamp range. Then unpause the ion beam quad and use the shift knobs on the manual user interface to adjust so the ion beam image is coincident with the electron beam image. In the patterning module under OmniProbe, check Insert OmniProbe to insert the OmniProbe. You can visually verify insertion of the OmniProbe on the exterior of the fib chamber. Activate the electron beam image, unpause it, and then mag all the way out. You should see the OmniProbe on the far left side of the image. Using the AutoProbe software on the second monitor, under Location Storage, select Eccentric High and then Go To. This moves the OmniProbe to directly over the center of the image, approximately 300 microns above the sample surface. When the omni probe has reached the eccentric high position, it can be brought down to the sample surface. In the auto probe software under probe controls, verify that stage frame of reference is selected. You can toggle between X, Y, and Z controls by selecting the middle square accordingly. Select the desired velocity from the list to the right of the probe controls. In this case, we have XY activated and we're using the electron beam image to move the omni probe so it is over the point of interest. Activate the ion beam quad and acquire a live image. In the auto probe software, change the probe controls to adjust Z and then hold the down button to move the omni probe towards the sample surface. As the omni probe approaches the sample surface, it will come in from the upper right side of the ion beam image. As the omni probe gets nearer to the point of interest, switch to the electron beam image, and then switch the probe controls to XY, reduce the probe speed, and adjust the omni probe position accordingly. Then switch to a live ion beam image, change the probe control to Z, and continue to bring the probe down to the area of interest. Repeat this process iteratively until the probe has reached the desired point of interest on the sample surface. When you are ready to extract the omni probe, enter the navigation module and then use the stage Z control to move the stage down to separate the sample surface from the omni probe. Then return to the auto probe software and under location storage, select Park and then Go To. Activate the electron beam quad and mag out as far as possible. Verify that the omni probe has reached the park position and is no longer moving. When the omni probe has reached the park position, enter the patterning module and then uncheck Insert Omni Probe to retract the omni probe from the chamber. You can verify this extraction visually by looking at the exterior of the chamber. When preparing lamellas for TEM analysis, it is common practice to reduce the ion beam voltage when performing final milling steps to reduce sidewall damage. If the ion beam voltage is set to 8 kilovolts or less, the ion beam can be directly aligned, which will result in the most accurate milling at lower voltages. Select Direct Alignments from the main toolbar. Then select L2 Modulator in the Direct Alignments dialog box. The image should start to go in and out of focus. Similarly to performing lens alignment, when using the electron beam, adjust the quad crosshairs to minimize shifting of the image as it goes in and out of focus. Once quad alignment has been completed, focus the image as best as possible using the manual user interface knobs. Then use the stigmator knobs on the manual user interface to obtain the sharpest image possible. Refocus and restigmate as needed until the best possible image is obtained. To navigate to the OmniProbe grid, activate the E-beam quad and acquire a live image. Then decrease the magnification to as low as possible. Then use the joystick to move to the grid. Once the grid has been reached, identify a post on the grid that will be used for attaching the lamella. In this case, we will select the A post, which is the farthest on the right of the 4 visible posts. Double left-click using the mouse on the A post to center it in the image. Note that for the most effective attachment of a lamella to the grid should be level in the electron beam image. As we can see here, this is not the case. To rotate the grid so it is level in the image, select the Stage pull-down menu and then XT Align feature. Follow the instructions in the dialog box to rotate the grid so it is level in the image. Then focus the electron beam image and link the working distance with Z. Then enter the navigation module and set the stage tilt to 26 degrees. If the grid moves from the center of the image after the stage is tilted, adjust the stage Z control to return the grid to the center of the image. Then change the tilt to 52 degrees, and again, if the grid deviates from the center of the image, adjust using the stage Z control. With the grid post now at eccentric height, return the stage tilt to 0. When the stage tilt has returned to 0 degrees, verify that the grid is being viewed perfectly edge-on. In this case, we can see that the grid is pitched slightly upward. You can then enter in a negative value for tilt until the grid is being viewed perfectly edge-on. It is usually not necessary to go further than -2 degrees in order to accomplish this if the grid was straight when loaded into the grid holder. Activate the ion beam quad and use the shift knobs on the manual user interface to center the post in the image. You can decrease the magnification of the live ion beam image to verify the post that you have selected for lamella attachment. To finish your FIB session, pause any live images that are currently being acquired. Then activate the e-beam quad, enter the beam control module, and select beam on. Repeat this for the ion beam quad. While still in the beam control module, select sleep to turn off the ion source. Navigate to the patterning module. Under gas injection next to PT depth, select warm to turn off heating to the PT GIS. Enter the navigation module and select loading unloading from the list of stored stage positions. When stage movement is finished, enter the beam control module and select vent to start venting the chamber. When the chamber is vented, gently open the chamber door, loosen the clamping bars holding each module in place on the universal mounting base, and then extract the modules. Then close the chamber door and pump back down under vacuum as described previously. Loosen each set screw holding each stub into the stub holder module. Then remove each stub from the stub holder module. To remove the grid from the grid holder, uncover the grid loader, then carefully remove the grid holder from the module, being sure to grasp it by its edges to avoid possibly damaging the grid with your fingers. Then place the grid into the grid holder with the whole side facing down. Tighten the grid holder to loosen the clip holding the grid in place. Then use a pair of vacuum tweezers to carefully grab the grid by its edge away from the posts that are holding any samples and gently remove it from the grid holder. Gently place the grid into a gel pack storage box. Then remove the grid holder from the grid loader and return the grid holder and all modules back to the storage box. Return the protective cover to the grid loader.